Alright, so I figured I should make a little video about the solution to test 3. So I'll just go through it pretty quick here. Problem number 1. The main issue whenever you're dealing with an integral in a complex domain is the question, the singularities that are apparent in the integrand, are they actually within the curve of integration? See, because if they're not, it doesn't matter. For example, this 1 over z minus 1, that's singular at z equal to 1. But this is the circle of radius 3 centered at 3i, and it does not pick up the singularity at 1. It's not within that circle. 2i, on the other hand, is, and the residue of this guy is just 1. So you get 2 pi I is the answer for problem 1. Problem 2, a little bit more exciting. So in problem 2, let's see here. Get my act together. Problem 2, got this rectangle here from minus 1 over to 2 and going from plus or minus 1 in the y. Alright. The thing is, pi over 2 is about 1.57-ish, and so only one of the pi over 2's fits within the box. The other one's outside, and of course there's 0 to deal with, which is an apparent. I mean, it's a singularity, it's an isolated singularity. So there are 2 isolated singularities, namely 0 and pi over 2. So I've got to face those for my residue theorem. But a little calculation here reveals that sine has a simple 0 at 0. And z cosine also has a simple 0 at 0. So when you take the ratio of 2 functions which both have a simple 0 at 0, the simple zeros in some sense cancel out. That's a removable singularity. So there's a removable singularity at z naught, z equal to 0 rather. On the other hand, the singularity at pi over 2, through I think rule 4 or rule 3, I forget which one honestly. One of them, their rules. We evaluate the top function, which in this case is sine of z at pi over 2, and then divide by the derivative of the denominator, which is z cosine z. Derivative of z cosine z is cosine z minus z sine z. Evaluate at pi over 2. That gets me a 1, division by minus pi over 2, which is minus 2 over pi. Then yield residue theorem finishes the job here. Let's see here. So I got my 0 from the removable singularity. There's no, the residue is 0. There is no, reciprocal term in the Laurent series expansion about 0. Because the Laurent series starts at order 0. And then over here, the residue of that was minus 2 over pi, so when you multiply these guys, excuse me, the pi's cancel, and 2 times 2 is 4, and there's a minus, so minus 4i would be the answer. Alright, that's problem 1, problem 2. Problem 3. Problem 3. What's going on here? Problem 3, I didn't mean for this to be tricky, but it seemed like it was tricky. So sorry about that. I put the z cubed on top to try to make it more interesting. I mean, in terms of like what the answer looks like, but well, anyway. So there's various ways to look at this, but I realized it was kind of silly. I could have just put like a z squared over z minus 1. It would have been the same problem, basically. So first of all, just algebra gives us minus z squared over 1 minus z. Alright. So dividing top and bottom by z squared and factoring in a minus 1. But then I can just leave the minus z squared out front, and then geometric series 1 over 1 minus r with r equals to z, give me that. And that's when the radius, when the r of the geometric series, Serios is not even a thing. Geometric series, the modulus of z has to be less than 1, of course, which is exactly our context right now. And so yeah, there you have it. This is the Laurent series for the power series, representing f of z between 0 and 1. Of course, in this case, this is an analytic function. It extends to 0 just fine, right? There it is. Now, the Laurent series on the exterior annulus outside of 1 is a little bit more exciting, because then I got to work on getting powers of 1 over z, because if I have 1 over z less than 1, that corresponds to modulus of z greater than 1, right? So I'm looking for reciprocal powers of z in this context. And so I just, you know, divide top and bottom by z, and that gives me a z over 1 minus 1 over z, which then by geometric series gives me this, which is that. And then I wrote things out and made a mistake, whited it out. So it's 1 over z to the minus 1 plus z to the 0 plus z plus 1 over z squared plus yada yada yada. So in this mess, only the first term, which is z, and the 0th term, the first term is n equals to 0. The second term is n equals to 1. So anyway, this are the first terms in the Laurent series, and then you get reciprocal terms, right? So the deal with infinity is the part which is not reciprocal is the singular part. So in this case, this does have a pole at infinity. The singular part at infinity is just the z plus 1, which means that it has a pole of order 1 at infinity. All right. So that was that. Now this one over here. Hey, come on. All right. Number 4. F of z sine z, meromorphic on c. What about, I forgot to answer the question here. What about c union infinity? It is possible that I need to give you guys back some points on this one. You can argue that with me at the final if you want. Now that I reread the question, I think you guys I might owe you guys a couple points in there, but it's probably irrelevant because I suspect very likely I'm going to replace your grade for this test with the final exam score anyway, so it may be kind of a moot point. You know, so forgive me for not reading my own question carefully enough. I was just focused on the C union infinity part when I graded. Anyway, so when you look at the power series for sine z, of course you got all these powers, odd, alternating, odd powers, plus minus. And when we look at the corresponding function at 0, which is f of 1 over w, g of w was the notation we used, well, you got infinitely many reciprocal terms, which means that it's an essential singularity at w equal to 0, which means that infinity is an essential singularity for f of z, which means that f is not meromorphic, as it has an isolated singularity which is essentially singular at infinity. Now, setting aside infinity, though, is f of z meromorphic on c? Well, yeah, sure. F of z is entire on c, right? It's analytic on c, which is even, that's a special subcase of meromorphic. So meromorphic just means all the singularities are isolated in poles, right? But the only functions which are meromorphic on the extended complex plane are rational functions. I almost proved that for you guys, I think, this semester. Now, let's see here. Calculate the residue of 41 plus 6z squared times the sinh of 1 over z. So I think, unfortunately here, like rules 3 and 4, those kind of things, they're just going to let you down. Here, you just have to use power series. You have to just do direct calculation of the series. And so the issue is we're looking for the 1 over z terms. So how could you get a 1 over z? When you multiply this times that, right, which is, there's the power series for sinh, evaluated at 1 over z. The only way you can get a 1 over z type term is the 41 times the 1 over z, or the 6z squared times the 1/6 z cubed. Everything else is going to be, what's the word? More reciprocally? I mean, if I do z squared times z to the 5th, that's like 1 over z cubed. And a 41 times that's 1 over z to the 5th. So there's only 2 ways to get a reciprocal in z term, which is what we define the residue to be, the coefficient of that term. So focusing my attention on that, I get this 41 over z and the 6z squared over 6z cubed, which gives me 41 plus 1, which is 42 over z. The residue here is 42. Not a surprising number to see on one of my tests. Let's see here. Don't worry, someday I'll find a new number. Joe, if you're listening, it will not be 7. Anyway here, So here we have determine the number of zeros for the polynomial p of z is z to the 6 plus 4z squared plus 13z plus 2 in the disk of radius 2. So what I noticed here was that if we put modulus of z equals to 2, then the modulus of z to the 6th is actually 64, and that is bigger than everything else that's left over. So if you look at the rest of the p of z, 4z squared plus 13z plus 2, less than or equal to that, which is at most 44 on the circle of radius 2, well, then we have that the z to the 6th term is bigger than the rest of it. All right, when we're at modulus of z equal to 2. But we also notice that f of z equals z to the 6th has a 0 over order 6, right? 0 over order 6 is 0, which means that p of z equals z to the 6th plus this other term, which is smaller than the first term in modulus, right? Likewise has 6 zeros, counting multiplicity within the z equal to 2 circle. And that, of course, is using Rochet's theorem. All right, let's see here. Let's see here. This one, calculate this integral via residue theory. So this kind of problem, you should definitely have a picture in your solution, right? No picture means that I can't entirely follow what you're doing. You know, you're like, well, we're just doing the same thing you were doing. Well, okay, but, you know, you should explain. I think I need some white out there. Oh, well, it's too late. It's already scanned. So I'm going to use the half circle contour again because it's going to pick up on the minus r to r, the integral of x squared over x squared plus 1 times x squared plus 4. And as r goes to infinity, we're going to argue that the integral over the top half circle goes to 0. And then the residue theorem is going to pick up two residues, one at I and one at 2i. That's kind of the big picture here of this problem. Specifically, here are the details. We can prove that f of z on the half circle, as long as the radius is larger than 2, we get the following estimate. All right, we get the following estimate, namely that the modulus of f of z is equal to r squared over the modulus of z squared times modulus of z squared plus 4. But that is certainly smaller than r squared. Excuse me, this is smaller than that, r squared minus 1 and r squared minus 4. That's like using the other triangle inequality, the one that makes it smaller. So you make the denominator smaller, thus making the fraction bigger. And then I drop the absolute values under the assumption that the r is greater than 2. So, you know, it starts out with like absolute value of the modulus of z squared minus 1. But the modulus of z is r, so that gives you r squared minus 1. But then you can drop the absolute value because we're assuming that r is greater than 2. So that's how I get from here to there. And then the ML theorem gives me that the integral is bounded by pi r, which is the length of CR, times the bound, which was r squared over r squared minus 1 times r squared minus 4. But you can count here 1, 2, 3, and the fourth order downstairs, 3 over 4 goes to 0 as r goes to infinity, which is good news. All right, then we just have to calculate the residues. So let's do that. Here's your residues. So I let h of z be z squared and g of z be z squared times z squared plus 4, so that I could use rule 3 explicitly. So I've got like h of I divided by g prime of I, h of 2i divided by g prime of 2i, which, you know, by this derivative here, if you think about plugging, let me scooch that down just a bit. If you think about plugging I into this, that makes this piece go to 0. If you think about plugging 2i into the derivative, it makes that piece go to 0. So that's helpful in terms of just simplifying the calculation, you know. So we get I squared over this, or we get 2i squared over that. It simplifies to minus 1 over 6i, or 1 over 3i. Put it all together. Integral over the boundary of the half disk is integral along the lower edge plus the integral around the upper half semicircle. And by the residue theorem, that's 2 pi I, sum of the residues. This works out to pi over 3. That goes to 0. This goes to the integral of interest as r goes to infinity, and there you have it. The integral is pi over 3. So this is not the easiest contour integration, but it's not the hardest one either, right? Far from it. No branch cut means not hard. Yeah, well, in my book anyway. But over here, I forgot to change the N to a K. My bad. My apologies. I don't think that actually confused you guys, but anyway. So we noticed that the function here, the complex function, is bounded in modulus by 1 over k cubed. But hey, that converges by the p equals the corresponding series for the terms 1 over k cubed converge by the p equals 3 series test, which means I can use these. 1 over k cubed is the majorant in my Weierstrass M test with, again, majorizing series p equals 3 test. So that gives me uniform convergence of e to the k over k cubed for modulus of z less than 1. Modulus of z less than 1 is the condition I needed to get this majorizing condition right there. All right, so that's the Weierstrass M test, which is definitely something you want to know. All right, now down here I squeezed the proof of both of these into the space, so the one is kind of sloppy, my apologies. So if you got a sequence of holomorphic functions which converge uniformly to f on d. Now what I should have done, I think our theorem was for a rectangle which was parallel to the coordinate axes, but I've said C is a closed bounding curve of a simply connected region, which is a subset of D. Anyway, let C be the curve that you like the most. You can make it a rectangle if you want. The point is, we integrate f over that curve. It's the integral of the limit of the sequence of holomorphic functions. But by the property that we proved for uniformly convergent functions, we can flip the order of integration and the limit, right? And so, I mean, that's what we had to do when we proved this theorem in the notes, okay? In the class, actually, I think. Although it was a few weeks ago, in what seems like a simpler time, I guess. But anyway, each one of these integrals is 0 because fj is holomorphic on D, and the property of holomorphic functions, in fact, a characterizing property, is that the integral around loops in the domain is 0, right? Or you could do rectangles parallel to the coordinate axes if you like. I think we had that as well. Anyway, so the limit of the 0 sequence is just 0, and so then we've shown that the integral of the limit function is 0 around an arbitrary curve in the domain. That means that f is holomorphic on D, which is what we were setting out to prove. Hooray! All right, now, this one down here, supposed to, if you have a 0 of order n for an analytic function, the proof is actually just a straight calculation based on, understanding Taylor series and all that. So you start out with it's analytic, so it's got a series expansion, right? Z naught is at order n means that the jth derivative of z naught is 0 for j equals 0 to all the way out n to minus 1. But then the nth derivative at z naught is non-zero. That's what it means to be a 0 of order n by definition. And then, oh man, see, I've already what's the word? I already scanned this thing. There's, as you see, you're going to have to put a little in right there. Anyway, sorry about that. So notice that the first n minus 1 terms are 0, so this is really some little n equals big N to infinity of that. But then I make a substitution. I just let, little n equal little n equal j plus big N. And that shifts the start of the sum from n to 0. Of course, infinity still goes to infinity. And the n, again, shifts to j plus n. But then I can factor out a z minus z naught to the n power, and it leaves me this series. Well, that series defines the h of z that we want. And that is, well, that's analytic, because there's a series expansion of it, see? And also it has h of z naught equal to 0, because h of z naught is a sub big N, which is, by the way, the big nth derivative at z naught of the original function divided by n factorial. That's Taylor's theorem. And that's non-zero because you were given that it's a 0 of order n. So sorry this is a little bit cramped in here, but I hope that gives you the sense of how you would have done that one. Now, the last problem, I tried to give you options, right? These are, four of the, I would say, more difficult integrals that I spent some time trying to explain. And, you need different techniques for different ones here, right? And I have explained all four of these integrals, although I did the, I have done it for beta in the previous lecture, and I have done it for arbitrary p in the previous lecture. This is just choosing p equal to a half. I'll remind you, I'm not going to talk through all this, but here they are. This is, I've talked through these before in my madcap hour of integration lecture. I don't know what you want to call it, but this is the, wait a minute, put these in order. So, so the integral of cosine of x over x squared plus 1, you can just use the semicircle, and actually that's probably the easiest one. But you do need to deal with the e to the iz thing and looking at the real and imaginary parts and all that. So there's a little bit more nuance here. Don't think we even needed Jordan's lemma to do this one. So, yeah. So since I had beta equal to 1, the answer to that question should have been pi e to the minus 1. Or just pi over e, you could say. The other one I offered was sine x over x. At least one of you remembered that was pi. Good job. Now this one we got to do the indented contour because the natural boundary, natural curve you'd like to do is like this, but you can't go across 0 because the function's not defined there. So instead you do this indented contour. You need the fractional residue. You need the Jordan's lemma, and yeah, all that works together. All that works together to give you pi. All right, so a little bit of a story there. A little bit more difficult. This one I think is a little bit even more difficult than the previous one because it's got a branch point. In other words, we had to use this indented contour we put the branch cut so it didn't interfere with the integration region. And we had to sort through how these different things were bounded, and after some effort we got minus pi over 4 down there. All right. So, and then again this one is the one that I went over, but in your test I had just square root, which would have been p equals to half, but exactly the same song and dance would have gone through here. So since p is equal to a half, the answer would have been p equals to a half. What happens with this formula? You get pi over 2 cosine of pi over 4, so that would be, I think it would be pi over root 2 would have been the answer for the problem on your test. But anyway, so I would encourage you to learn how to do those. And of course you need to look over the old test. The final is comprehensive. I will post the PDF of the scan of the solution in the course content. Of course, keep in mind I forgot to scribble that in there, but I don't think you guys will be fine with that. So anyway, all is not lost. There's still the final. Don't be too discouraged. All things are still possible. Just come to terms with what went wrong on this test. So I left your test with the in the help center, so you can go pick it up there. Okay. So anyway, thanks.